Alright, so small perturbations of the thrust forces and moments then. So as always, the notation for a small perturbation is the lowercase version of that particular variable. So here you can see perturbations in the longitudinal forces and moments, lowercase f sub tx, f tz, and lowercase m for the pitch moment due to thrust. And then perturbations in the lateral directional forces and moments described by lowercase fty, and then also the roll and yaw moments due to thrust. And what we see is, as we described with the aerodynamic forces and moments, that in the longitudinal sense, these perturbations in the longitudinal sense are functions of the forward velocity and angle of attack, whereas in the lateral directional sense they are functions of the side slip angle. So as we did before, we need to non-dimensionalize the forward speed u based on the steady state velocity vector. And then you've seen this so many times already now. We apply a Taylor series expansion to each of these functions, right? And we're left with this system of equations, which is written in terms of partial derivatives. So let's take one of the longitudinal forces, so in the x direction, partial derivative of the thrust force in the x direction. This is the non-dimensionalized u. That partial derivative is evaluated at the steady state condition multiplied by the non-dimensional u, and then the same thing again, partial derivative but with respect to angle of attack, evaluated at the steady state condition multiplied by angle of attack. So this again is another application of the Taylor series expansion. The longitudinal ones are all done with respect to these two variables, the non-dimensional u and alpha, whereas the lateral directional ones are just expanded about the angle of side slip. So what we can do, as we did again in the previous chapters, is write this system out in terms of the thrust coefficients, which we are going to define down here. So the thrust force in the x direction is the thrust coefficient in the x direction multiplied by the dynamic pressure multiplied by the wing reference area. And then some variables are non-dimensionalized with respect to the mean aerodynamic chord. Some are so that's in the longitudinal sense, and then the other ones in the lateral directional sense are non-dimensionalized with respect to the wing span. So what that allows us to do, or what those definitions allow us to do, is to write this system in terms of those coefficients, which we have up here. So where we've replaced the force vector in each of these equations by the corresponding coefficient, and now we have all of these q bar s terms floating around, right, which came from these definitions down here. So we need to do a little bit of work on these, starting with looking at what this particular partial derivative is here, which crops up in each of these three equations. So to discuss what happens to the dynamic pressure with respect to this non-dimensional u, we need to consider how we defined the dynamic pressure, right? So we define that as a half rho v squared, and if we're considering a small perturbation in v, we have the steady state velocity vector plus small perturbations in u, v, and w, right? So that's what I've written right there. And then if we apply the partial derivative to q bar here, we end up with vp1, which comes from here, and then essentially we're just taking the partial derivative of all of this stuff with respect to small u. So that's what we've got here, vp1 multiplied by the partial derivative with respect to small u of all of this stuff from up here, right? And then we can cancel out the u and the v and w terms, and then we end up with, we're cancelling out the v and w terms because we're taking a partial derivative with respect to small u, so all of these terms cancel out, and we end up with this expression here. So if we evaluate this, which is the partial derivative of q bar with respect to the non-dimensional u, at the steady state condition, that means that u here is 0 because we're at the steady state condition, right? So we have no perturbation in u. So then we're just left with rho times vp1 squared, which if we use our definition of q bar from up here, look, we can just write that as 2q bar. So using that expression for the partial derivative of q bar with respect to the non-dimensional u at steady state condition, we can replace this thing, which we've just found, into each of these three equations here in the longitudinal sense. And then we end up with this system, which is a little bit neater. So the coefficients here have just been written with the subscript to denote the partial derivative with respect to. Again, this is a technique that we used in the modelling of the aerodynamic forces and moments. So, for example, if we take this first one here, the partial derivative of ctx with respect to the non-dimensional u, we can just write as ctx sub u, and so on and so forth, and then we end up with this slightly neater looking system here. But the problem is here, so now what we have is all of these coefficients which have cropped up. There's actually 3, 6, 9, 12 of these in this system, and we need to just kind of denote or consider what each of these coefficients represents. So first of all then, the ones with respect to x. So we have ctx1, ctxu, and ctx alpha. So these are thrust coefficients, but they correspond to different conditions. So the first one is the thrust coefficient, which opposes the drag coefficient in the steady state equilibrium condition. So this is the one that basically opposes our drag. So thrust equals drag, the drag coefficient in the x direction at the steady state condition. The second one, ctxu, is a thrust coefficient which depends on the small perturbations in forward speed. So again, this one is highly dependent on the propulsion system and how that engine operates depending on the different speed that we're flying. So think back to the descriptions of the different power plants that we discussed in class, right? And then finally, ctx alpha is a thrust coefficient which depends on small perturbations in angle of attack. Generally, we can consider that to be approximately 0. The next one is the thrust coefficients which depend on so steady state condition, small perturbations in u, and small perturbations in alpha, but in the z direction. Generally, these can be considered as 0 unless we're using some kind of thrust vectoring method. But if we're considering all of our thrusts to be equal, then we can consider these ones to be approximately 0. So then moving on to the CM terms. The first one, obviously in the trim condition, we can consider the pitching moment coefficient to be 0. So if the thrust axis is aligned with the XS axis, but in general, obviously the thrust pitching moment should balance with the aerodynamic pitching moment in a trim condition. Otherwise, we'd end up with some kind of pitching moment, which we wouldn't have in a trim condition, right? We have an equation here to work out the pitch moment coefficient due to thrust and how that changes with respect to small perturbations in u. We have an equation to calculate that, which is basically the force multiplied by the moment arm, where we describe the distance in the z direction from the center of thrust of the engine to the center of gravity position of the aircraft. And that just gives us a non-dimensionalized moment arm with respect to the mean aerodynamic chord. And then, so the final term, the final CM term, is the CMT alpha, which generally we can look up for typical aircraft in typical regimes from a table in this Roscam reference. And that's going to be different based on the type of power plant, again, mainly due to whether it's a propeller or a jet engine type power plant. And then finally, all of the terms, thrust coefficients with respect to beta can generally all be considered to be 0 because of that symmetry of forces that we were discussing in the previous video. So there we go, that's how we model small perturbations of the thrust forces and moments.